In-class activity 12A, graphing polynomial functions. Imagine a roller coaster traveling along the section of track as follows. The coaster starts at point A at time t is equal to 0, and it reaches point B at time t equals 2 seconds. It takes 3 additional seconds to complete the loop and finish at point C. 1. On the axes provided, sketch the graph of a function h that gives the height of the coaster above the ground at the time. So we have the axes here, and if we think about part A, we're going to start here, and notice that A and B and C, they're all pretty much the same height above the ground. So at part A, what does it say? It travels, it goes up, and then it comes down to point B in 2 seconds. So here's 2, so it's going to go up slightly, and then come down to roughly the same height that it started. And then it takes another 3 seconds, so 3, 4, 5. It'll finish at second 5, and it's going to go from B, it's going to go up this way, reach a maximum or a top height, and then come back down there, and then finish at C, right there. So we're going to go up from here. Let's see, go up to a maximum height, and then come down to finish. Whoops, maybe I should have come down a little quicker. Let me try that once more. There we go. So that's roughly, this is the time axis, and this is the height axis. And there's our quick sketch of what happened there. Oops, doing all sorts of things with the pen that I didn't mean. Okay, let's get back to this. Objectives for the activity. You will understand how to model the position of an object with polynomials, the advantages and limitations of modeling with polynomials. You'll be able to use a graphing calculator or app to view the graphs of polynomials, setting viewing windows appropriately. Use a graphing calculator or app to investigate the features of the graph of a polynomial. 2. Suppose that the height in feet of the roller coaster in question 1 is modeled by the polynomial function listed here. It's listed as h of t. I'm going to scroll up to the next page. I'll leave I'll stop at 2. So part A, it says use a graphing calculator or app to plot the graph of h. Set the viewing window so that you can see all the important features of the function over the first 5 seconds. Sketch the graph and label both axes. Okay, so I'm going to go to my calculator app. Let me just close this, open this here, go to my y equals screen, and I have it listed here under y1. So I'm going to open up y1, and then I'm going to graph it, and you're going to see that you can't see anything because we have to set the appropriate viewing window. So the viewing window, it's going to go from 0 to 5, and let me just go back to here, and I'll go second window. The x is going to start at 0, and then it's going to go up to 5, and we can count, the scale can be by ones, and then the top height, I'm going to go up to about, let's see, the y-axis, so I'm going to go to 80, and we're going to count by 20. Scale is 20, that's good. Let's try to graph this and see what we have. Second, whoops, graph, there we go. So starting on the horizontal axis, we go from 0 to 5, 0 to 5 seconds. And then the height axis, it goes up from about 14 or 12 or so feet up to almost 80 feet. And we can even move this around a little bit. There we go. Now it asks us to sketch this. So keeping that in mind, I'm going to go back to my drawing here, and I'm going to try to draw this fairly accurately. And this is our time axis. This is our height axis. And we started not quite at 20 feet, but whoops, Let's see, we're going to go up to 80. Right in the middle will be 40, 20, and 60. And let's see. If I draw that, we're going to start below 20 because it was about 14 or 12 or 14 that we started. And then we're going to go up and come down. And then we're going to go up and then come down like that. Let me try that once more. There we go. So it looks something like that. Rough, very, very rough sketch. Part B. When is the coaster at its highest point? And how high is this point? Well, let's go back to our picture over here. And the highest point, let's see, I'm just going to go here and see if I can go all the way around until I reach a max. So it looks like it's at its highest point at about 79.4 feet. And then that happens when the time is about 3.8. So let's go back to where we were. When is the coaster at its highest point? And highest point, it's going to be, let's see, about t is equal to, we said 3.8 seconds. And how high is this point? It's about, we say 79.4 feet. All right, part C. On what time interval does the roller coaster make its fastest descent? And explain how you arrived at your answer. So let's go back here to the picture. And what I'm looking for is a descent. So I want to know when the graph is going down. And it looks like it's going down the steepest. If I just grab this and I look over to the right here, it looks like it's going down, that last part of the graph from 3.8, it would be to the right. So let's go back here, open this up. On what time interval does the roller coaster make its fastest descent? It looks like it would be from about 3.8 seconds all the way to the end, which would be 5 seconds. And it's just the steepest part of the graph that's going down or decreasing on that interval. And that's how we arrived at that answer. Let's go to part D. Examine the behavior of the graph of h outside of the interval between 0 and 5. Could this function make a good model for the height of the roller coaster after t is equal to 5 seconds or before t is equal to 0 seconds? Well, let's see. I'm going to go again back to the graph, and I'm going to, let's see, let's move the window around again. I'm going to go second window, and the minimum value here for x, let's go, I don't know, go -5. Max will go up to 10. Y minimum, let's go, I don't know, -10. We don't have to change that at all, but we'll just leave it at, oops, let's get messy now. We'll leave it at -5 and see what happens. If not, we'll come back and fix it. So let's go to graph. Oh, wow. Okay, outside of the interval. Let's see, if we look to the right, like after t is equal to 5 seconds, the graph goes way up, way too high. So no roller coaster is going to realistically be that high. And same thing on the left. It's too steep and too high. So let me go back and write some of this down. It says examine the behavior. Let's see. Could this function make a good model for the height of the roller coaster? I'm going to put a big no there. And it's just not going to make no roller coaster could go that high. No coaster can go that high. Let's go to part 3, and I'm going to move this up so we can see the whole question. Another amusement park ride travels along a straight track but reverses direction several times. The riders start at point S at time t is equal to 0, and their distance to the right of point S at time t is given by the function s listed here. A negative value of s of t means that the riders are to the left of point S. Okay. Part A, use a graphing calculator or app to plot the graph of S. Set the viewing window so that you can see all the important features of the function over the first 20 seconds. Sketch the graph and label both axes. Okay, so back to the graphing calculator, and I'm going to go done. What I'm going to do is go back to y equals. I'll turn off my first graph, and I've already entered in under the y2 screen, or y2 row, the next function, and let's see what happens when we graph it. Okay, that's going to be, oh, it's part of the graph, but let's set the window. Let's do better than that. And let's see, graph, zoom, standard, not good either. So we'll go back to second window, and the x values, let's go negative, oops, and I don't know how I got there. Delete. X minimum, we're going to start at 0 and go to X max, we're going to go to 20. And we can go, scale can go by 1, sure. Y minimum, let's go, this is where we went negative 120. Y max will go up to positive 120. And scale, we can go by 20, sure. So let's graph this and see what we get. All right, so that's what that curve looks like, at least on that section or that interval. And part A was use a graphing calculator or app to plot the graph, set the viewing window, which we did. Over the first 20 seconds, we want to see what's happening. So we have the X, or the horizontal axis for the first 20 seconds going 0 to 20. And then we want to sketch this. Okay, so that's what it looks like. Let's go back to the drawing here, or our drawing. And we're going to go like this. And let's see, we went to, was it 100 or 120? And then we went negative 120. And then we have a curve. I can do better than that. Let me try it again. All right. So it looks something like that. Very rough sketch. So this is our time, and this is our distance axis. Part B, when does the ride change direction? When is the ride moving to the left? Okay. The ride changes direction at time, let's see, back here. Let's reach our max there, about 3.55. So that's where it's going to change direction. And let's see this going down all the way down, then it reaches a minimum. Whoops. There we go. And that looks like it's going to be a minimum at time 14, that's 14.22 seconds. And it's moving to the left between those two values. So let's write this down. Go back here. When does the ride change direction? Let's see. The ride changes direction at t, that was about 3.55 seconds. And t is equal to 14.22 seconds. And the ride's moving to the left between these two times. Okay. between these two times. There we go. Part C, describe the motion of the ride over the first 20 seconds. The following diagram represents the track. Imagine the ride moving along it, starting at point S. Label the points where the ride reverses direction. Label the distances between the points on the diagram, including S, and then along with the time values that correspond to each point. Okay, so we can do this. There we go. So if we start at S, that's going to be t is equal to 0. All right, and then we're going to be moving to the right. There we go. And then we change direction at t is equal to 3.55. It reverses direction at which is about 74.3 feet to the right of S. Okay. It continues going left. So we're going to start here. Continues going left. It's going to pass point S. And that's going to pass it at, from our graph, we would see that it passes at around 8 seconds. So let me put that t is equal to 8 seconds. And it continues going left. Let's see how far, until 14:22. That's another time that we had. It reaches the other point. So why don't we call this, I'll call this point R and this point L. There we go. Then it reverses direction again and continues to the right, passing point S again. And I'm just basing this on our picture or the screen that we graphed. So we're going to go back this way. And then it's going to be about what? T is equal to 18:22 or 44, excuse me. I looked at the other twos there. So it should be a 44. And end up here about 19.56 seconds. All right, part D. Examine the behavior of the graph of S outside the interval between 0 and 20. According to this model, what happens to the ride as time passes? Are there any other limitations to the model? Let's see how we could answer this. After 20 seconds, let's see. I'm going to go and bring up this again, and let's work with the window. So 0 will go -10, and then let's go to 30 and see what happens. Okay. After 20 seconds, the ride continues to the right at a faster and faster speed. Wow, okay. This is unrealistic because the track must have some finite length. It can't go on forever. And another limitation is that the ride starts immediately moving pretty fast and without gradually accelerating speed. So back here, and what could we write here? After 20 seconds, the ride continues to the right. I'm just going to go back here to the right at a faster and faster speed. And that's unrealistic because the track must have some finite length. Okay. All right. And that concludes this video. Thank you.